Hi, it's Chris Tedder here, and today we're going to look at the Meyers asymmetric alkylation, and that's Meyers with only one E, not M-E-Y-E. Pretty confusing if you get those two mixed up, so just one E. So the overview of this reaction is that you have a pseudoephedrine auxiliary, which is this part of our starting material that's been acylated onto the carboxylic acid you're trying to add something to. So then you've got a base, LDA is a really common one, lithium chloride, which the lithium's just been shown to increase the yield and effectiveness of the reaction, and the alkyl group you're trying to add with a halogen attached, usually bromine, iodine, chlorine. So key intermediate here is it forms the Z-enolate when the base triggers the enolate, and that means that the new group has to be added down in this direction. And then the mechanism's not fully understood about why it actually ends up being the stereochemistry it does. But the key point is you get, if you order your first atom here where we added the new group as 1, we get 1, 2, 3, 4. You get a 1,4 syn relationship between your new group and this R group that's part of your pseudoephedrine auxiliary. So that's the key point you need to take away, and this was outlined by Meyers and colleagues in this paper when they fleshed out the details of this reaction. So let's look at an example in a total synthesis. So our literature example comes from this paper, and it's in the total synthesis of minus acylactomycin. Probably pronouncing that wrong, but it's an antibiotic they isolated from some bacteria. So the example used in this literature is they start again with the pseudoephedrine auxiliary, except they've got the other enantiomer this time. Does not matter, works the same way. Got LDA, lithium chloride, THF for a solvent, and this is the alkyl group they're adding, so you can do it with more complex groups. And here's their product, and I've rotated that back into the plane, but before we rotate it, we get this geometry, which gives us our 1,4, in that case, syn relationship. So we see it works the same exact way, and then we just rotate the large group back into the plane, so the methyl that was there at the beginning is now going back. So that's the example from literature, and it ends up making this stereocenter in the final product. Now, I know that's going backwards, but that's just because when they closed this 11-membered ring, it ended up flipping the things, but this is the stereocenter they made with that reaction. So that's the literature example from the total synthesis. We got one more thing to look at, which is how we get rid of this auxiliary to go then do further reactions. So let's take a look at that. So with all chiral auxiliaries, we have to take them off eventually. And you can do that by either just treating with an organolithium reagent to just do a substitution on your carbonyl for the auxiliary. You can treat it with lab or lithium amidohydroborate and get your primary alcohol from your carbonyl. You can do a 1-to-1 mixture of H2SO4 to dioxane and get the carboxylic acid back. Or you can treat it with lithium triethoxy aluminum hydride in THF with some HCl and get a ketone at the end. So that's the overview of the pseudoephedrine chiral auxiliary in the Meyers asymmetric alkylation. Thank you.